Okay, part C of the question says, how long will it take until 1 million bacteria are present? Now, if I actually compare my answer in part B to what the question is asking in part C, you'll notice that in 24 hours, or in one day, we got 20 million bacteria, and we're trying to figure out how long it takes for only 1 million bacteria. So I know for sure my answer will be less than 24 hours. So let's start by looking at the equation. So I have B of t equals 5,000, 2 to the exponent t over 2. And what I'm trying to solve for is how long it will take. So this tells me I'm looking for a time. And what I'm told is the number of bacteria. So this part here represents B of t. So I'm going to replace B of t, which is the number of bacteria, with 1 million. And the right side stays the same. And I'm going to try to solve for t. Now again, just like we talked about before in lesson 5, what you want to do is try to get the exponential part by itself. And we can do that by eliminating the coefficient part. And the way you would eliminate the coefficient part is to divide both sides by that coefficient part. The operation here is already multiplication. The opposite of multiplication is division. And on the right hand side you get 2 to the exponent t over 2. And on the left hand side, 1 million divided by 5,000 gives you 200. That's not so bad a number. We can work with that. And so now what we're going to try to do, much like what we talked about in lesson 5, is the only way to compare these two numbers is if their bases are the same. So we're going to try to write 200 with the base of 2. So 2 to some exponent will equal 200. And so we're going to play around a little to try to figure out what that number that would go in the exponent would be to make it 200. Okay? So 2 to the exponent 5 is too small. So 2 to the exponent 10 is way too big. So we got to backtrack a little. So let's try 2 to the exponent 8. Still too big. 2 to the exponent 7. Too small. So it's somewhere between 7 and 8. So 2 to the exponent 7.5. Okay, closer. We need to go a little bit higher. 2 to the exponent 7.6. Even better. 2 to the exponent 7.7. And we're a little bit too high. So 2 to the exponent 7.6 was our best bet. We can get a little bit closer. 2 to the exponent 7.65. That's pretty good. 2 to the exponent 7.64. And I think I like 2 to the exponent 7.65. Okay, so what I did is 2 to the exponent 7.65. Okay, so you got to play around with this a little bit just so you can get your exponent to work. And, oops, I must have pressed something weird. And that's the one that was pretty close. So I like that number. I'm happy with it. So that's the one we're going to use. Okay? So what that means is I can rewrite 200 as 2 to the exponent 7.65 is equal to 2 to the exponent t over 2. And because the bases are the same now, I can compare the exponents and ignore the bases. And so what that means is, therefore, 7.65 is equal to t over 2. And finally, if I'm just trying to solve for t, to get rid of a denominator of 2, I just need to multiply both sides by 2. And I end up getting t equals 7.65 multiplied by 2 gives me 15.3. So that means it'll take about 15.3 hours for the bacterial population to reach 1 million. And if I compare it to part B again, like I said, the number of bacteria in 24 hours is 20,480,000. But we only wanted to know how long it takes for it to become 1 million. So, because this is much less than 20 million, we knew it'll take much less time than 24 hours. Okay? So therefore, it takes about 15.3 hours for 1 million bacteria to be present. running out of space. Okay, but you get the idea.